The J1 lesson focuses on confidence intervals for means, plus we'll be doing a few other problems spiraled throughout the year. Starting with number 1, most recent tests and calculations estimate at the 95% confidence level that the maternal ancestor to all living humans called mitochondrial Eve lived 273,000 plus or minus 177,000 years ago. What is meant by 95% confidence in this context? So we're interpreting the confidence level, and from your notes, this would be your H1 notes. If you use a C% confidence intervals often, about C% of your intervals will capture the true parameter value. So these ones are talking about like Z values, and this is totally wrong, that the probability, we really don't talk about probability when talking about confidence intervals. And this one is very limited. If 20 random samples are obtained by this method, then they said, oh, the true age will be in 19 of these. That's too specific. We have to say for many, many intervals. So 95% of all random samples of data obtained by this method will yield intervals that capture the true age of mitochondrial Eve. E is the correct answer. Number 2, 1 gallon of gas is put in 30 test autos, and the resulting mileage figures are tabulated with the mean of 28.5 and a sample standard deviation of 1.2. Determine a 95% confidence interval estimate of the mean mileage. So first of all, let's look at the t distribution, which we use for means. And I put in 29 degrees of freedom because there are 30 test autos. You always turn that down by 1. And if this is the t distribution on Staplet, so it gives me a nice visual here. And there's my middle 95%. And if I were to use my calculator to calculate this, so I have the number here from Staplet, but you need to know how to do the calculator. Well, inverse t on the calculators, even the fancy ones, only do left-sided. They do percentiles. So we have to add in this 0.025. That's 2.5% on this side, because we have 5% split between the two areas. So this percentile is not the 95th percent. It is the 97.5th percent. So to do it on the calculator, it's inverse t, area is 0.975, and it will ask you for degrees of freedom, which is 29. So we get 2.045. Now we need to go ahead and calculate the standard error. So that's basically going to be our sample standard deviation divided by square root of n, which is 0.219. Then our confidence interval is our point estimate plus or minus our critical value times our standard error. So we have 28.5 plus or minus 2.045 from here and 0.219 from there. Multiply those two out, and I get 0.448. If I add 0.448 to this, it gives me the high end, 28.948. If I subtract 0.448 from here, I get the low end. And so that is answer C. But here's the good news. When doing multiple choice, you can definitely do a shortcut using the calculator. So we're going to hit Stat, go to Test, and we're going to do a t interval because we're dealing with means. Hit Enter. We have a choice between data and stats. So if I had data, it would let me put in a list, but I actually have statistics, including the mean and the standard deviation. So the mean, they said, was 28.5. And the standard deviation is 1.2 for the sample. And sample size is 30 because there are 30 test autos. And confidence is 95%. Hit Calculate. So you can see there's your interval, 28.052 to 28.948. That's it. Number 3, the number of accidents per day at a large factory is noted for each of 64 days with a mean of 3.58 and a standard deviation for the sample of 1.52. With what degree of confidence can we assert that the mean number of accidents per day at the factory is between 3.20 and 3.96? So let's go ahead and first write down our margin of error formula, which is the two ends of your confidence interval divided by 2, because we know the two ends here, and margin of error is half the width, or 0.38. Now we also are going to go back to this margin of error formula, which is, it's also the critical value times the standard error for the sample. We know that the margin of error is 0.38, and I know the sample standard deviation is 1.52, and the sample size is 64, so we take square root of 64, and we get 0.38 equals to the critical value times 0.19, divide both sides by 0.19, and we get 2 as the critical value. So we're going to go ahead and practice this on the calculator using TCDF. First, you go to second distribution, and instead of normal CDF, we're looking for something with a T, and you can see it down here, number 6, TCDF. We have our critical value of 2, which means we're starting at -2. Make sure to hit the negative sign, and going up to +2. And then we have 64 days, so we're going to go 64 minus 1. I think that'll work. We'll find out. I could put 63 in there, and let's hit calculate, and voila. So we find out that our area is 0.9501, or this is a 95% confidence level. First, so we select 95% confidence level, and there you go. Number 4, what sample size should be chosen to find the mean number of absences per month for school children to within plus or minus 0.2 and a 95% confidence level if the standard deviation is 1.1. So we've got first our margin of error formula. Hopefully that's starting to become pretty familiar. It's your critical value times your standard error for your sample, so that's a T star. And so we're going to use Z equals 1.96 to start for T star. Why is that? Well, we don't have a sample size. That's the whole point of the problem. So we're going to just assume that it's 1.96 using the normal distribution. We go ahead and we substitute in. So there's my margin of error, 0.2, 1.96, 1.1. Then I multiply that out. I can cross multiply, solve for n, and I get 10.78 is the square root of n, but I need to square that. So I get 116.2. Now, usually what I would do if this was free response is I would be tempted to go find the T star using a degrees of freedom of 116, say for a 117 size sample, and you could refine it more, but I don't see that being tested so much, and this is a multiple choice sample, and this is the highest value already, so E is definitely the answer. But if they had some higher values, I would be tempted to go ahead and recalculate my T, because this would be, maybe it's 2.05, maybe it's 2. So again, you could recalculate it. You're probably still going to get very close to the same number, but it might be slightly larger. So that's the strange thing about sample size for means. You start out with a Z to establish what it is, and then you can actually do another iteration where you do the T, because now you have a starting point for the degrees of freedom. Number 5, suppose you do 5 independent tests of the form the null hypothesis mean is equal to 38 versus the mean is greater than 38, each at the alpha of 0.01 significance level. What is the probability of committing a type 1 error and incorrectly rejecting a true null hypothesis with at least one of the 5 tests? So since we're setting the alpha, we're setting the probability of a type 1 error, and this assumes that the null is actually true. Otherwise, you can't commit a type 1 error. So alpha is 0.01. So then we're going to find the probability. Oh, there's your answer. We're going to find the probability of at least 1, which is the same as 1 minus the probability of 0 errors. All right, so that would be this. Basically, where the 0.99 come from, it's a probability of not making a type 1 error. So it's 1 minus 0.99 to the 5th, which happens to be 0.049. Number 6, given an experiment with the form mu equals 35 and versus mu is less than 35 and a possible correct value of 32, you obtain a sample statistic of the mean being 33. After doing analysis, you realize that the sample size n is actually larger than you first thought. Which of the following results from reworking with the increased sample size? So we're looking at probability of type 1 error, probability of type 2 error, and change in power. So most of these are a decrease in power, but some of these are an increase. So first of all, let's go back to that activity we looked at with power and the election results. So if you recall, in their fictional scenario, you have the two distributions. This is our null, which works out because it's about on the same side. And there's our alternate, where this is true or this is true, right? So if our sample size increased, so we looked at increasing sample size, which tightens up the distribution, and these were the new curves that were drawn. So you can see what happens is your power goes up. So it's an increase in power because you're more likely to correctly reject the null, right? And then you have this tightens up, so you have a less likely probability of failing to reject. That's your beta. Personally, I'm not so sure that there's a change in your probability of type 1 error, just because you set the alpha. So assuming you set the alpha to a certain value, unless maybe they said, oh, it's the same cutoff point. So the alpha might go down if you were using the same cutoff like we were here, instead of, so that's a scenario where C would be the correct answer, all right? Number 7, one ESP test asks subjects to view the back of cards and identify whether a circle, square, star, or cross is on the front of each card. If P is a proportion of correct answers, this may be viewed as a hypothesis test with P equals 0.25, and the alternate is that it's greater than 0.25. The subject is recognized to have ESP when the null hypothesis is rejected. What would a type 2 error result in? So our two hypotheses are our subject does not have ESP. That's what we should assume. And then our alternate is they do. So type 2 error is what they're looking for. So we're saying 2 is really true. The subject really does have an ESP, but we make an error. So we think the other one, the first hypothesis, is true, which means he does have an ESP, but we don't recognize that he has ESP. Number 8, suppose we have a random variable x where for the values k equals 0 through 12, the associated probabilities are blank. So this big formula, what is the mean of x? So hopefully you recognize this from your math chart. This is the formula for a binomial distribution. And you can see, and we have the formula for the mean right here, it's n times p. So if we go n must be 12 and p must be 0.34, we can just multiply those two out and we get 4.08. So C is the correct answer. 9, which of the following statements is incorrect? Always fun because we have to go through every statement. A, the range of the sample data set can never be greater than the range of the population. That's true. The most extreme values are the max and the min of the population. While the range is affected by outliers, the interquartile range is not. True. IQR is not affected by outliers. Range definitely is. Changing the order from ascending to descending changes the sign of the range. So that's false. Range is always max minus min, not last minus first. And then D, the range is a single number. Yes, it's whatever you get from the subtraction of max minus min. And IQR is the width of the box containing the middle 50% of data, so that's true. So the only one that is incorrect is C. Number 10, a researcher planning a survey of heads of household in New York City has census lists for each of the 62 counties in the state. The procedure will be to obtain a simple random sample of heads of households from each of the counties, rather than grouping all the census lists together and obtaining a sample from the entire group. Which of the following is not a true statement about the resulting stratified sample? So A, it says it is more susceptible to bias. Well, stratified is just simple random sampling of different groups, so there's no change in bias. This one is not true. Additionally, stratification does help make it easier and more cost effective because you have your people grouped by area already. It gives you comparative information that you might not have for different counties, and it recognizes that the opinions of heads of households are different in different areas. So our answer is A. Number 11, a government statistician claims that the mean income level of families living in subsidized housing is $9,250 with a standard deviation of 2575. A report plans to test this claim through interviews with a random sample of 50 families. If she finds a sample mean more than $500 different from the claim 9250, she will dispute the statistician's claim. What is the probability that the reporter will mistakenly reject a true claim? So one of the students said, hey, I thought type 1 error was equal to alpha. It is. And here she didn't really set an alpha. So what we're doing, she set a difference as whatever was significant. So we're going to have to calculate the probability the old-fashioned way. So our mean is 9,250. And our standard deviation for the, or standard error for the sample is 2575. All right. Well, that's actually population standard deviation. I take that back because it says, claims that. So just a little FYI, population standard deviation. So this is a known value. So we're going to use a normal distribution here. All right. She finds the sample mean is more than $500 different. So we're going to have a cutoff here and a cutoff there. Now, we're looking for the probability of rejecting. So we're looking outside of the area. So this is just showing it. Here's my 9250 and my 364.16. And then if she has an answer out here, she's going to reject the claim that the value that they make is 9,250. So this is the probability of rejection. Now you can calculate it with your calculator, but you're going to have to do just one side. So say the lower is negative infinity, that should say negative, to 8750. We get 0.085, which is pretty much what I have here, but that's only one side. So we have to double it, and the answer is C, 0.170. Number 12, a nursery owner claims that a recent drought stunted the growth of 22% of her evergreens. A botanist tests this claim by taking a simple random sample of 1,100 evergreens and finds that 268 trees in the sample show signs of stunted growth. So the null is P is 0.22, which she claimed, and the alternate is that it's not 0.22. What is the value of the test statistic? So our P hat is the 268 over 1,100, which is 0.244. Then we're going to calculate our standard deviation for the sampling distribution, right? And that will be your statistic minus your parameter. So, and notice I'm using the 0.22 in here because we do have a claimed value. Anytime you have a claimed value, that's what goes in that formula. Then our statistic is 0.244. We subtract 0.22, and so that matches C. Number 13, a union spokesman is trying to encourage the college faculty to join the union. She would like to argue that the faculty salaries are not truly based on years of service, as most faculty believe. She gathers data and notes the following scatter plot of salary versus years of service. Which of the following correctly interprets the overall scatter plot? So if you look at these first two, faculty member with fewest years of service makes the lowest salary. A faculty member with more service than another has a greater salary than the other. Those are about individual data points, and we want to interpret the overall scatter plot. And then the next two say there's either a strong or no clear relationship, but we can see there is a moderate relationship, but I would not call it strong. So E correctly interprets the overall relationship. While there is a strong positive correlation, and it said little deviation. I'm not sure if it's strong. Anyways, there is a distinct deviation from the overall pattern for faculty with fewer than 10 years of service. This looks moderate to me. Strong moderate, maybe. Who knows? Okay, number 14. So E is the correct answer. Number 14. The travel miles claimed in a weekly expense reports of the sales personnel at a corporation are summarized in the following box plot. Which of the following is the most reasonable conclusion? The mean and median numbers of travel miles are roughly equal. Well, this is pretty obviously skewed left because we have some outliers to the left. We have a long whisker, so odds are it looks skewed left. We're not 100% sure because it's box plot. But that means that the mean and median are not roughly equal, probably. And the mean number of travel miles is probably less than the median. So A and B are not true. Next one says most are between 0 and 200. Well, 0 to 200 is less than 50% because it'd be right there, right? 0 to 200, so we're not hitting the median yet. Then it says most are between 200 and 240. So that would be this area. Definitely contains more than 50%. So let's just check the last one. It says the left and right whiskers contain the same number of values. Well, if there were no outliers, then I would agree with this statement, but we're missing a couple of data points because of these outliers in that whisker. So this whisker has a few more data points. So the correct answer is D. Number 15, a study on school budget approved among people with different party affiliations resulted in the following segmented bar chart. Which of the following is the greatest? Well, it's a segmented bar graph, so we don't know any of the numbers in each group. These are only going to 100%. So you can cross off A, B, and C, which means you can also cross off D. So the answer is, it is impossible to determine without additional information.